To introduce our sixth speaker for the day, we now request Mr. P. Sendil Kumar, Chairman, IIF Chennai Chapter, to introduce Mr. Anandan Pari, Technical Director, Scaanray Digital.
Good evening, everyone. Hope everyone is awake. We will organize the next session. Please bear with us. It's a privilege to introduce our next speaker, Mr. Anandan Pari, a highly accomplished professional in the field of non-destructive testing, with a career defined by technical excellence and industry leadership. Mr. Anandan brings wealth of expertise and deep academic foundation to the session, holding a bachelor's degrees in mechanical engineering and MBA with specialization in finance and marketing. As a certified NDT Level 3 professional, he possesses mastery across multiple critical techniques, including radiographic testing, ultrasonic testing, magnetic particle testing, and penetrated testing. Currently, he serves as Technical Director on NDT Level 3 at Scaanray Metallurgical Services, where he leads the delivery of advanced inspection solutions to the industries. His specialization consultancy work is also vital to the automobile and die casting sectors, particularly in ensuring regulatory compliances and implementing AERB guidelines. Beyond this corporate leadership, Mr. Anandan is a pillar of professional community. He has served as a secretary for the Chennai chapter, not IIF Chennai chapter, and Chennai is a joint secretary at the national level of Indian Society for Non-Destructive Testing, where he has been instrumental in advancing the NDT ecosystem through technical initiatives and professional development programs. In addition to his technical achievements, he has also contributed his leadership to the Tamil Nadu Cricket Association across various committees. Please join me in welcoming Mr. Anandan Pari. Thank you.
To 3D drawings, which gave us a fantastic overview of how a computed tomography will look like. So once when I was discussing with Mr. Bakul, we said let us not overlap two topics which will be boring for the audience over there. So what I thought was, we have an expert in CT, so let him talk on expert, and I will take you back to the primitive method, how it all started, like the film radiography and the transition which is happening presently from film to digital. Many of my customers used to ask me, industrial NDT is nothing but a mirror copy of what the medical imaging is all about. But when you see the kind of advancements which we have happening in the medical, we don't seem to be getting that in the industry. Still, we are still in the film-based radiography with a little bit of the digital advanced by top corporates like the TVS group of institutes and Hyundai group. So we see why it is, because if you say take a human body, it's more of 70% of water and the bone density, which is going to be varying between among us. But whereas if you take the industrial component, the geometry changes between the steel castings to the aluminum castings. We have from a 2-inch gate wall body to up to 64-inch gate wall body. So to design a technique or a system to radiograph it, it becomes difficult. So that is why in the weld segment and primarily to a certain extent of aluminum components, digital radiography has been successful. But still, steel castings, it has still been a challenge. We have been able to achieve the sensitivity level of up to iridium 192, which is up to 40 mm or 50 mm of wall thickness. Still with cobalt and very high energy like LINAC, we are still not able to get the same sensitivity which the film gives you. So with this small introduction, so what I will do is, my topic is going to basically cover like how the transition is happening, but still I will say that film has been predominantly used, but a slow transition is happening, and why it is happening, how it is happening, and I'll give you a small brief, like if you are planning to go for a digital radiography system, what are the requirements, and the most important part will be the regulatory aspect, because these are radiation generating equipments, and radiation generating equipments require the approval from the Atomic Energy Regulatory Board. So I'll just give you a brief walkthrough of what it is. So this is just going to have 9 portions. First is what is X-ray and how it operates. So this is a X-ray mechanism is something which works on the absorption technique. For example, different materials have different absorptions. So based upon the absorption technique, the X-rays, the film produces between a gray image and a black image. So why this transition? I know now morning when we were talking about that CEO's conclave, they discussed about the aluminum prices are going up, and because of the war, we have also seen a massive hike in the silver prices. The silver prices, which were at 80 rupees a gram, is now hovering around 280 to 300. So how does it matter with film radiography? Film has two major constituents. One is silver halides and other is polyester base. Both of them are derived out of it. So because of that, today the film prices have jumped close to about 120%. Like how Karthikeyan sir said, they were ready, many of the customers are ready to bear the hike, but some of them are still not able to bear. The second one is chemical. Many of the companies now are having low chemical treatment plants. When film radiography, the chemicals are alkaline and acidic, so they would not like to have it with them. Slow turnaround time. Any job which you have to do it with film radiography takes minimum of 60 minutes for you to know what is the output. The exposure time will remain the same, whereas the development time with the developing and fixing and the film to dry with the normal drying process, it takes at least 1 hour. So your productivity is hampered. You will not know whether the defect is there or not. No digital enhancement. When there is going to be difference in thickness, you cannot alter your contrast or brightness. The film is a film. You can only increase the brightness in your viewer, so which is not going to give you any better image. Film storage. If you take a very big corporates, they have a separate rooms with controlled air conditioners, so that the film has to be retained for minimum 5 years. And if it is going to be for a nuclear industry, the film retaining is going to be for 10 years. And for 10 years, the film has to be kept safe. And after 6 years, if the customer wants you to retrieve it, and they give you only 2 days time to get you that joint details or that casting details to be given. So storage and archival is a very big problem in film. And radiation dose. The comparatively, when you take film radiography, if the exposure is going to be 1 minute, when you go for the digital or the computed radiography, the exposure rate is going to come down. So 1 minute exposure time on a film radiography can be made between 20 to 30 seconds, which automatically increases the productivity, and the person who's operating it gets lower dose. So now, if the cost of the equipment is going to be high, so what is the next method? The next method is called digitize the films. This is what is being utilized by many of the weld industry, where the analog films are being converted into digital mode. So what happens? Existing analog for die casting are retrieved from the archives. Tomorrow you want to retrieve it, as I told you. After 5 years, when the customer says you want this, you just put that joint number or the radiography number, the film comes in front of you, so you don't have to. And no more storage of radiographs. You can discard the radiographs, and archival and retrieval becomes easier. And if you run this file in a volume graphic software, it can give you the output as how our Karthikeyan sir had explained in the morning. So from film, the next step what we get into is called computed radiography. Computed radiography is a system where instead of film, we will use something called as phosphor imaging plates. These phosphor imaging plates will acquire the data from the X-rays, and then these phosphor imaging plates have to be scanned in a scanner. Then what happens? The image is giving you in a DICO NDE format, which is a DCM mode, which can be stored and retrieved. Once the image is being captured into the system, you can go into the next stage where you can erase it. The advantages of this is this can be reused multiple times. The maximum which the manufacturers are giving an warranty is 1000 times. So again what happens, you have better productivity, so that a single image plate can be reused 1000 times. You can use the existing X-ray source, you don't have to go for a new X-ray source. Wide dynamic range eliminates the chemical processing. So what happens is, in film radiography, if your output is going to be in 60 minutes, here the output can be in 10 minutes. It's DICO compliant and no post-processing chemical treatments. The next option from computed radiography we move on to is called digital radiography. So there are two types of flat panels which is here. One is called on the direct conversion and on the indirect conversion. So this is how the digital radiography system will work. It works on a CC system. Say for example, your sample is there and the X-ray source is on this side and the DDA is on the other side, and it has been controlled by the manipulator. So the C is something which is like this, so you can move it up and down. Okay, sorry. So this is your X-ray source and this is a DDA, and the manipulator, this can move up and down. Your sample can be fixed. This can be customized according to your requirement. Like if you want it to be 2 axis, they can give you 2 axis. If you want it to be 7 axis, they can give you 7 axis. At some parts, you can even have your samples to be tilted. So based upon the customer requirement, this can be changed. And this is the DDA. This DDA is going to be rigid, and the size will be like 40 by 43, 30 by 43, or 12 into 16. There are different few sizes available based upon your component size, your lead cabinet size. This can be designed. So the advantages of film over the digital radiography: you have image display time in 5 seconds. As your radiation is on, the image gets captured in your flat panels, and outside operator sits and he will be able to get your image in 5 seconds. So what started at 60 minutes in film became 10 minutes in computed radiography, and now it has become 5 seconds and less than 5 seconds. You can stop when you want when you have acquired the image completely, you can manually stop the radiation. So the dose reduction is 50 to 80%. As I told you, at 1 minute to 5 seconds. So your dose is phenomenally reduced by 80%. So your life of your tube is much increased, and automatically the person who's operating is going to get lesser dosage. You can archive it, so it is for easy retrievability. So these are a few calibration checkpoints which I have added, because since it is going to be on a die casting, and many of the customers of die casting industry have DDA machine, but they have not been able to, they have been using it in such a way that, okay, we go in the morning, the operator will switch it on, and then they'll start acquiring the images. But a few of these, as I speak, because I'm a consultant for Atomic Energy Regulatory Board, the customers used to say like, what are the checkpoints? So I've just briefed down a few checkpoints. First is called the dark image calibration. This is performed without a radiation exposure. You just go switch on the equipment, see how your DDA is planning. Second is gain calibration. It should ensure that your uniform pixel range is captured properly. Bad pixel mapping. There will be a lot of pixels which is available in the DDAs. So some pixels over the period will not be working properly. So you have to know which pixels are working, which pixels are not working. Image quality metrics. Your signal to noise. As your signal is better to the noise comparatively, your image is better. If your noise is more, your image gets disturbed. Spatial resolution. The spatial resolution is used using the duplex IQIs. Detector sensitivity. It measures the dose response, image lag, geometrical and calibration. Finally, at what frequency these has to be done? There are a few things which says you have to do it daily, and few of things which can you do it monthly. This is how the recording medium has evolved. Right from our film. Film, it was a photochemical reaction which has a silver halide, and then we went to the image intensifier. Image intensifier has not been so popular in the market because this is the place where the X-rays are converted into light. This has been predominantly used by Bharat Heavy Electricals Limited, but on a commercial end, it has not been a successful one. Next became computed radiography. This is a successful product presently available in the market because it can be bent like a film, whereas the DDS are rigid and fixed. And then you have the digital detector arrays where the X-rays are converted into light and then to electrons. And the next thing happening is called the photon counting, where the conversion of photons to electrons. This is the one which is presently in research. They have not yet been made much into commercial production yet. So we'll just see how it is on the die casting applications. So these are the few defects which are there available, which is according to our ASTM E2422. One is gas porosity, shrinkage porosity, cold shuts, misruns, inclusions, and hot tears. This is a few image which taken up on welding, which is the lack of penetration, porosity, lack of fusion, cracks, slag line, and the tungsten inclusion. This is with the die casting, gas holes, a shrinkage, inclusion, and an unfused chaplet. So once to overall summarize how it compares between film, computed, and digital. Image medium is a silver halide. It's a single use. It cannot be used. Computed radiography, as I told you, it is a reusable phosphor imaging plate. Digital radiography, it's a flat panel detector. Again, it is reusable. Acquisition time 60 minutes, which is including processing. Computed radiography, it is 5 to 15 minutes. Here, it is less than 5 seconds. Dynamic range, it is up to moderate. This is wide and this is very wide. Resolution 200 lines per mm, and this resolution of 200 lines per mm you cannot change it. It is fixed. It is up to 25 lines per mm. Here what happens is you have different types of imaging plates which is available. You can go for ultra blue plates, which gives you even some imaging plates which has a resolution of up below to 10 lines per also. Same thing goes with digital radiography. You have up to 10 lines per mm. Chemical processing, for film it is required. For digital and computed radiography we don't require. Radiation dose, if you keep a baseline of 100%, for computed radiography it is 50% and for digital radiography it is 20%. Recurring cost, the film radiography is high because the film you have to, once you use a film you cannot reuse it. For computed radiography it is low, and for digital radiography it is very low. But here very low in the sense your initial investment is going to be high, but this is going to be on the recurring cost. Digital archiving, with a film radiography you cannot digitally archive it until or unless it has been digitized using using an industrial digitizer. This is full DICOM archive and this is also full DICOM archive. So automation is, with film I don't think you can automate anything because it is all manually done. Computer radiography you can try to make it automated, but whereas with digital radiography with the C arm you can automate it as per your willingness. One of at Brakes India Schollinger unit, they have automated in such a way that one component is being radiographed around 24 locations in 8 seconds, and it is completely automated. So how much ever you want, as per your requirement, the manufacturers will be able to automate it. Only thing is the cost will be high, but it is achievable. So once we move on from here, we have to see what is the regulatory framework. What does the Atomic Energy Regulatory Board say? So one is the safety code for industrial radiography. Governs the use of X-ray and gamma ray equipment for NDT, establish the dose limits and qualified personal limits. Radiation protection. It mandates the radiation survey, classified areas, personal dosimetry, dose limits, where it says it is only 20 millisievert a year, which is for a radiation worker who can take that much amount of radiation in a year. And record keeping of all radiography operations. The next one is on the radiation surveillance and area classification. Defines the controlled and supervised zones, mandatory TLD badges allocation, radiation monitoring instruments, and periodic workplace surveys. Finally, equipment and facility licensing. All X-ray and radiography equipment must be registered with Atomic Energy Regulatory Board. This is a mandatory requirement. Generally, what happens when a corporate, because as Karthikeyan sir said at the last moment, the cost is very high. So many of the corporates during the board meetings, they think how do we allocate the fund and how would, and they discuss all these things, and then they finally arrive, okay, let us allocate it and we will start. So what people don't know is, to get an AERB approval, it takes anywhere between 9 months to 12 months, right from the start A to Z until you order the equipment, which many of the corporates forget. They think, okay, we'll order the equipment, let the equipment come, but the equipment will lie idle either at the customs or in the warehouse. So the general breakdown of what it is to get your institute registered into the portal. For the first step, it takes 30 days. Then recording of the name, 25 days. Layout approval, where you want the X-ray equipment to be placed, and what is going to be the surrounding manpower, which is what is going to be the public, or whether it is going to be only radiation workers. So there are going to be 3 drawings, which is going to be the cross section, which is going to be the elevation of the enclosure, and where your X-ray equipment is going to be placed, and that drawing, and that has to be indicated in the complete layout. And after you get the approval of the layout, if the management decides to change the place of the cabinet from one place to another, they have to go for a reapproval. So we have to have an emergency preparedness plan. The emergency preparedness plan is what happens if the door doesn't get closed and the X-rays start generating. So what is the emergency plan? We have it in plan. Next is the security. What happens if an unidentified person operates it? These are all which we say that how it is going to happen. We are not going to say it is going to happen, but what is the plan we have for that? Once we have all these approvals, then happens the procurement of radiography device. So after all these steps, we go for the NOC. So you have already identified. So the supplier will give you his AERB identification number for the equipment. So then you go the RT device purchase order to the supplier, the letter of the contract awarding party, again the security plan, copy of undertaking by the supplier who says that if at all there is going to be any problem, once you purchase the equipment, we are going to service it, service and maintenance NOC, and radiation monitoring equipments. The radiation monitoring equipments are the radiation zone monitor. What is the radiation which is going to be in the zone of the X-ray machine? You need to have survey meter, you need to have dose meter. Dose meter will be like one for the operator and one for the company registered employee who's going to be responsible for it. So 2 dose meters are required. And once you have the NOC approval, you give that NOC from AERB to the manufacturer. So manufacturer will initiate the movement. Again, the movement from the manufacturer's place to the corporate's place have to be registered. So that comes under the movement permission. Moving of the X-ray machine after the issue of NOC. So once the equipment comes in, we have to give the equipment receipt notification saying that the equipment has come in with a photograph of how it has come in and the delivery challan. Once it is all done, we give a permission to use the radiography enclosure. So during the installation, the manufacturer will come and they will do a radiation survey. With the radiation survey chart along with the manufacturer's RSO and our RSO, the radiation survey report carried out by RSO should be submitted. So once it is done, finally we will go for the license for operation. So the license for operation will get 30 days. So we will approximately it is 30, 55, 85, 105, 125, 145, 165 and 185. These are minimum. Before this you will not get permission. These are minimum days. So it is 185 days, which is 6 months. So if one document is mistaken this, again it becomes another 25 days. So minimum period taken for any approval is anywhere between 9 months to 1 year. So this alone you need to take it up in mind. So what are the compliance checklist? Obtain AERB equipment registration for each unit. What happens is, it is not possible, but once you decide that this equipment is going to be there, we need to have type approval, like how Karthikeyan sir had explained during his presentation that his equipment is type approved. Most important is type approval. Before you discuss with your customer, you should ask him whether it is AERB type approved. Appoint a radiation safety officer, which is mandatory for facilities using ionizing radiation. So here what happens is, many of them get confused between level 2. Everybody says I am an RT level 2. What does an RT level 2 mean? RT level 2 is SNTTC 1A level 2 who is not approved to be an RSO. RSO is somebody who is a level 2 as per BARC. This is a specific examination which is conducted only by BARC in association with IDEMI in Mumbai. Nobody else is conducting this program in India. So the candidates have to go to IDEMI, get them, and it's a 45-day course where they'll teach upon all the radiation process and what happens when the in catastrophic solution. So very important is basic difference between SNTTC level 2 and a BARC level 2. If this is very important, so that tomorrow when you are hiring somebody, you have to be very clear. You have to say that you have to be a BARC level 2, which is called the site in charge program, or an RSO program. Design radiation enclosures to achieve 1 millisievert. This anyways they would have, your manufacturer would have achieved it. Install radiation warning signs, interlocked entry doors and warning lights. Issue TLD badges to all classified workers. These TLD badges are being issued only by AERB approved companies. For Tamil Nadu it is Aventech, which is in Porur. So these TLD badges will be allocated to all the radiation workers, and it is mandatory for them to wear it during radiation, which will give, as the radiation gets exposed, the badge will be recording the radiation which they have got it. So accordingly, once you send it to Aventech for reading, at the end of 15 days they will be giving us the data. Maintain calibrated survey meters, conduct quarterly radiation surveys on workplace and maintain records. Ensure all ADT radiographers hold valid BRC certificates. As I told you, they should be RSO, BRC, or if it is going to be level 1, it is called BRC level 1 certificate holder. Maintain logbook for all exposures, components, anything, and obtain prior AERB approval for layout change. As I told you, if you plan to change the layout and plan to shift the equipment from one place within your factory, you have to again go for an AERB. So the transition roadmap. So what happens is, I'll just make it very small, brief in this. As I told you, first of all, what is the quantum of job you have? Whether the quantum of job can be done using digital or using film. And once you have that quantum of job for digital radiography, then we'll go ahead. And most important part of it is your RSO, your radiation safety officer. So because this radiation safety officer appointment comes in phase 3, which is month 4 to 7, and which he has to be there, and you will be paying him a salary just like that for 8 months, which is we cannot avoid it. That is what the AERB tells. So the final summary is, film radiography imposes chemical storage throughput and dose burdens. CR offers a low disruption entry path using existing X-ray sources. DR delivers the maximum throughput and automation for high volume die casting inspection. Cabinet X-rays are accepted by AERB when properly licensed and operated. AERB compliance is mandatory. RSO appointment, equipment registration, shielding approval and dosimetry. Digital radiography dramatically improves defect recognition, like how sir had explained to you, and image archival and audit traceability for die casting. Thank you. Any questions? You can go ahead.
Any questions, gentlemen?
Mr. Anand, you said when we go for computed radiography, you would have films that you'll convert to digitize.
Yes.
Would it be possible to adjust contrast?
Yes.
So that you could highlight the porosities and all those while you're doing it?
We can.
So your films might be dark, but you can adjust contrast.
See, it is actually like gray values. See, there will be around 60. It is up to, like, in your film density, you call it 2 to 4 density. In the 2 to 4 density, once your film is 2.5 density, we cannot change that, the density in the film. Once you go to computed radiography, it is the imaging plates which you get scanned. So once you scan it, you can do the brightness and contrast adjustments. So if you have around 25,000 to 30,000 gray values, it should be enough. You can do the brightness contrast adjustments.
But typically the older films that we have,
yes,
if you're going into the past, and we have the film.
No, you're talking about digitization.
Ah.
Yeah. Now go ahead. Sorry. Yeah.
So when we do digitization, would we be able to extract more information by adjusting
It is very
contrast?
very difficult, because what is there in the film is getting converted,
Right.
but some part of it, if it is too good, yes, we can do it, but it's a 50-50 case. If the density is going to be like 3.5, we may not be able to do it much, but we can give it a try.
Only if it is lower.
Lower.
Oh.
Thank you, sir. All right. Thank you for the lovely session, sir. I now call upon Mr. M. Balasubramaniam, Head Marketing, GR Metal Alloys, to felicitate Ananda sir with a traditional Angavastram and a specially curated gift.